means at least it's getting to one participant. That means it ought to be going to the remaining participants. But let's verify for sure, maybe while I note a couple other announcements here. After the course is over at noon, you can go either two ways to obtain copies of the slides if you wish, or to, of course, one thing for sure you want to do is download your certificate so that you can prove to the various licensing groups that you took this course today. And and then there's also a quiz that will happen afterwards, and I'll ask, I'm not exactly sure how PDH Source is going to administer that quiz, but I believe there's a quiz, and you will watch the message box to make sure that some announcements comes up about that. Okay, 1, 2, 3, 4, 5. Everybody can hear. Okay, thank you, folks. And I guess in this case I can say thank you, gentlemen. I don't see any ladies in the audience here. So I'm also assuming you can see the title slide on the page. We confirmed that ahead of time. Electrical trends, electric vehicle charging, home automation, and Powerwalls. That's what we're going to be talking about today. And I guess a lot of the stuff in this presentation is going to be based on my opinions, but my opinions are generally, as an engineer, I don't like to just have opinions unless I have some basis for them. Times are changing. They've been changing for a long time, haven't they? I mean, the transportation ideas have changed. Communication ideas have changed. I think I first learned to type on a typewriter like that. Even the way we compute things is different. You don't see very many of those K&E, log, duplex, decitrig slide rules around these days. And lighting, of course, has gone from candles to kerosene lamps with mantles, all the way up through LED and CFL. Well, let's say LED, which is the current technology, 10 times more efficient than typical incandescents. So the direction we're headed is efficiency, and there's some very interesting ramifications. So let's take a look at what we want to talk about today. Certainly the trends have been from inefficient to efficient. There's a major trend going on right now from fossil to renewable. Florida Power and Light, which is my electrical service provider down here in Florida, are now at the point where their carbon dioxide emissions are very close to what they would be with methane alone. They're getting rid of their coal, they're moving to natural gas, but they're also building a lot of renewables. And that's happening all over the country, and not just all over the country. In fact, the matter is all over the world. China is building something like 5 times as much photovoltaic as the United States was last year. They're slowing down a little this year because of the coronavirus. We'll see what the result of that is yet to, come forward. Dirty to clean, pretty important transition. Predictable to less predictable. That's not particularly a desirable situation, but fact of the matter is, it is predictable that the photovoltaics won't make electricity at night. But when the wind blows is a little bit less predictable, so that's just something we're going to have to deal with. And mostly this will be dealt with by increasing the amount of energy storage available. And we'll be talking about energy storage towards the end of the presentation today. There will very likely be more high voltage DC transmission lines installed, and more control and data analysis. Big data is the big thing these days. I retired from Florida Atlantic University in 2005, but I maintain relatively close contact, and I know that a lot of their graduate students are accepting jobs at NextEra Energy, just up the coast from us, and they are doing some very interesting things there in terms of the one PhD student happened to have his expertise is big data, massive databases. And so that's what the utility industry is kind of all about. And of course, I think we could also add to the list that there will be more distribution. We'll see more distributed energy as well. So let's take a look at what's out there here for a minute. This is the growth of worldwide energy production by source. The key here, this is worldwide. Most of the things we'll be talking about today will be United States, but a lot of people are feeling like, gosh, the United States has to do all these things. What about the other countries? Well, the fact of the matter is, China's ahead of us on the installation of renewables. I guess I already said that. Two particularly interesting lines to look at. You'll notice the coal, oil, and natural gas on the top there, up in the 100 quad range. Quad's a measure of energy to 10 to the 15 BTUs is a quad. Kind of difficult to get a handle on, but when you talk about coal, oil, natural gas, hydro, and whatever, you need some common dimension to be able to compare them. So the interesting thing is that green line at the bottom, because it is climbing very quickly. And if you project that out, notice the star there is where it was in 2016. And fact of the matter is, the 2018 is right on that green line as well. And where it's going to continue, well, there's no reason to believe that that green line is not going to continue up, such that by about 2030, the total energy production, that is in kilowatt hours, of renewables will be comparable to the total energy production of all of the fossil fuel sources, the three on the top. And the other thing that's happening is the projections of coal being level is probably not accurate. It would appear that the coal may start to decrease. That one's still a little bit unclear. It's kind of a matter of how quickly the Chinese replace their coal, because they really don't like this stuff very much. They found out it makes the air pretty dirty. And so when you have the Olympics threatened, that's a problem. Anyway, when we talk about replacement of fossil fuels with renewables, what this graph, the green and the blue, by the way, is hydro, which is considered renewable, but it's separated out from the wind and the solar and the biomass that are the traditional renewables. And the bulk of that green line is wind and solar. So it's out there, and it's energy sources. The change in these sources is going to involve additional work for the architects and engineers who are currently at work. And I'm assuming that those who are participating in this webinar, are exactly in that position. So there are four things that are going to probably result in some major changes in grid use. And these four things are going to be providing a fair amount of work for engineers and contractors. Electric vehicles, for example, energy efficiency. Almost everything is becoming more efficient. It's amazing that there's I wouldn't have believed this 10 years ago if somebody told me there was going to be an air conditioning unit, a heat pump, in fact, with an SEER of 33.1 on the market in 2020. And it's there. So amazing stuff is out there that we need to keep up with. Otherwise, we won't be serving our clients as well as we should be, because almost all these things are very cost effective. All right, distributed generation, energy storage, again, talk about that at the end. Smart grid, smart homes, that's part of what we're talking about today. Okay, so let's move on and let's talk about electric vehicles. You see up there, electric vehicles really have two classifications, all electric. You can see that white BMW, that's a nice piece of change for that machine. But then BMW's got that cute little one in the lower right also that not nearly as expensive. And if any of you are on Long Island, they've had a major incentive program to get people to buy these up in Long Island. And that's a nice little all-electric BMW. The silver one is a Honda Clarity. The telltale on this one, as you see on above the rear wheel, is the gasoline, and the front wheel, that opening there, is for the electricity tank. So you got a gas tank and electric tank. And the other electric vehicle up on the top, what is that? Is that Toyota? Sorry folks, I can't recognize what that is. I took the picture myself, and now I'm not sure what it is. In any case, all of these vehicles need to be charged. And so there's some interesting work for the electrical engineers to determine whether there needs to be a service change. Typical charging on electric vehicles, about every hour of charge gives you about 5 miles of driving if you do it on 120 volts. But anyway, let's move in and look at some of the math for that. Okay. First of all, what is an electric vehicle? And we can go to the National Electrical Code to determine that. Starting out with passenger automobiles, that's kind of an obvious one, but there are also electric buses, trucks, and vans out there. Some of you may have seen a picture of the Tesla pickup truck. It's a pretty modern-looking vehicle. Neighborhood electric vehicles look kind of like golf carts, but they're certified for use on the street. There's electric motorcycles. Electric golf carts, by the way, and forklifts, they have to be classified as an electric vehicle. It has to be authorized for use on the street. And golf carts aren't supposed to be driven on the street. And also electric vehicles must use a rechargeable battery. So even though hybrids have traction batteries in them that take over part of the ride, in the modern hybrids will run on batteries, but those batteries get recharged by burning gasoline. So, and also, of course, with regenerative braking. In any case, hearing aid batteries don't qualify for electric vehicles, so we'll kind of disregard that possibility. All right, we get some busy slides coming up here now, but it's maybe useful. Maybe everybody knows this, maybe not. Let's read through it together. I realize everybody can read, but if we read it together, then that makes sure I leave enough time for everybody to read it. So, hybrid vehicles have a combination of gasoline engine and an electric drive motor. They have a 12-volt battery, just like every other automobile out there. It takes care of the lights, the starter, because you got to start that gasoline engine at some point. And then there's a high voltage battery pack to supply the drive motor. This battery pack, kind of an average, somewhere around 500 volts DC. Everybody's is a bit different, but a little bit higher voltage so you can have less current to run in the electric drive motor. When a hybrid vehicle is run in the economy mode, when you stop the vehicle, the engine stops. And there's a big reason for that, because about 15% of normal driving involves the engine idling. So the idling stops. And if the charge in the batteries goes too low, because of the air conditioning running or anything else running, headlights, who knows, It'll start up again automatically, so that's not something the driver is concerned about. But it is interesting to note that the engine stops. So that's one reason why hybrids get more mileage. When you start up the electric motor, depending how fast you want to start up, in some hybrids, the electric motor does all of the acceleration, and the gasoline engine gives the motor a boost. Because the electric motors have a pretty significant, they're DC motors essentially, and they have amazing starting torque. You can really get up to speed in a hurry. Dynamic braking involves converting energy and motion to electricity. So that's a pretty neat thing too, because just take your foot off the gas and all of a sudden, as you slow, the energy of slowing down, that kinetic energy that's being lost is being converted. A goodly percentage of that kinetic energy is being used to partially recharge the batteries. And all the battery charging for a hybrid comes from the gasoline-driven alternator or dynamic braking. There is no external charging on a plain hybrid. All right, so a lot of you already knew that, but now everybody's aware of that, and we're all on the same page. Okay, so there are two types of electric vehicles out there. There's the all-electric, and the range of the all-electric vehicles is somewhere between 100 and 400 miles. And the battery storage capacity for these vehicles is somewhere between 30 kilowatt hours and 100 kilowatt hours at the moment. The Nissan Leaf is down around 30, I think, and the 100 kilowatt hours is the big Tesla. 100 kilowatt hours, that's a lot of kilowatt hours. Most of the batteries are lithium. I'm not aware of anything that's not lithium. And the charging time depends on the level of charging, which we'll talk about later. The plug-in hybrid is what people like I happen to have, because I wasn't sure about if I were trying to take a longer trip in this automobile. I wasn't sure whether I'd find a place to plug it in, so I wanted to make sure I had a gasoline backup. Turns out we're getting over 500 miles to the gallon because most of our driving is around town with that vehicle. And only occasionally do we get on the highway where we need to turn on where the gasoline engine turns on. So as a result, we can get up to about 400 miles on the car. The electric only range is typically about 50, and the battery pack is somewhere in the 17, 18 kilowatt hour range typically. And again, depending whose vehicle you buy, they may be different from that. So if you take the 50 miles electrical and the 350 mile gasoline range with that 8-gallon gas tank, you get about 400 miles before you have to either recharge or gas up. Charging time depends on the charge level, and therefore we'll talk a little more about that. So let's just look at cost. And the reason we're doing some of these things is one reason why people buy these things is because they're looking for cars that are less expensive to run. Some people feel like they want to reduce their carbon footprint, whatever the reason. But if we look at a full-size SUV at 20 miles a gallon, here's your assumptions. They're $2.75 a gallon gasoline and 15 cents on a kilowatt hour electricity. Again, kind of averages. In Florida, we're paying around 12 cents a kilowatt hour. Gasoline right now is up around $2.90 a gallon. And of course, as you know, these things fluctuate. So, but once you know what those numbers are, you can move on and calculate your operating costs of the vehicle. So full-size SUV, 20 miles per gallon, 1,000 miles is 50 gallons of gas, so that's $137.50. You got a small SUV with 30 miles per gallon, your operating cost for 1,000 miles drops to $91.67. That, of course, doesn't count any other maintenance on the car. So there's your story with those two cars. Add a couple other cars. A hybrid sedan at 55 miles a gallon, which is pretty typical these days. Some get more. And again, this depends how you drive it, just like any other car. Well, this particular sedan in 1,000 miles uses only 18.2 gallons of gas, so it's cost you $50. A electric vehicle or plug-in hybrid electric sedan, operating electric only, and typically these vehicles get somewhere between 3 to 4 miles per kilowatt hour. So in 1,000 miles, that means you'll use 250 kilowatt hours at 15 cents. So your cost for fuel, so to speak, is $37.50. The plug-in hybrid operating half and half, 500 on gasoline, 500 miles on electric, is going to use a total of $46.25 worth of fuels between gas and electric. Okay, let's just hold up just a minute now. Let me remind everybody, let's see who's here. I believe somebody new came in. We've got 8 participants now. 1, 2, 3, 4, 5, 6. Oh, okay, that's PDH Source and Roger Messenger as well. Okay, so let me remind you that if you want to break in and ask a question or make a comment, feel free to click on that conversations icon. It's the one that looks like a dialogue thing for a cartoon. And it's right below the participants icon, I believe. And or you have the option of there's also an icon with a question mark in it, I think, which is also activated. One or the other of those. Just type in your message, hit enter, and I'll see that message. So that if you want to comment or ask about any of these things we're talking about, it's a pretty convenient way. Then we'll be able to discuss anything you'd like to discuss in more detail. Okay, so now we can talk about charging levels. Charging level 1 uses a 120 volt outlet, and it charges at somewhere between about 1,200 to 1,400 watts. Now, the double E's, the engineers, probably almost everybody in the group knows the National Electrical enough to know that if you've got a 15 amp, 120 volt circuit, you're not supposed to draw continuously more than 12 amps, which is 1,440 watts. So if you have a dedicated 15 amp circuit, you can probably charge at level 1 your vehicle. We happen to have a 20 amp circuit down in our garage of our condominium that has a few trickle charges and a few other things plug into it. But when we plug in at night, it's fine. We didn't have to go to the bother of having a special 240 volt circuit pulled from our meter room out to where we park our car to be able to charge up. There was already one there. If you've got a single family detached, you likely have a 20 amp circuit available in your garage that very likely can be used. All right, now we're going to talk about what you get for this, but right now we're just talking about charging levels. Level 2 uses either 208 or 240 volt single phase outlet. Depends on what your service is. And it charges somewhere in the 3,000 to 7,000 watt range. All right, so if you have a 3,000 watt charge at 208 volts, that's 14.42 amps. So you need a 2-pole 20 amp to handle that. If you're charging at 7,000 watts at 208 volts, then you're going to need a 40 amp circuit, 2-pole 40 amp circuit. 3,000 watts at 240 volts, a little bit less, but you still need that 20 amp circuit. And 7,000 watts at 240 volts is 29.2 amps, so you need a two-pole 40 amp circuit. So you're looking at number 8 wire. Okay. You can see the plug-in up on the top there. That's that 120 volt connection I was talking to you about. But this one on the bottom has the same kind of connection. There is standardization now among the connectors for electric vehicles, reasonable standardization, such that the public electric vehicle charger on the lower right there has the same kind of connector that connects up to the electric vehicle as the one that you got when you bought the car. And the car itself is, at least to my understanding, it's the car that decides what level it wants to charge at. So that's why you can use the chargers that are out, say, at some of the public libraries. We've got at least one charger in the cell phone waiting lot at the Palm Beach International Airport. Some of the government buildings have installed electric chargers for electric vehicles. And I'm guessing that up north, you probably see more charging stations than that. But there's still, in the next 10 to 20 years, starting today, we're going to see a major upsurge in the number of vehicle chargers that will be in public spaces for people to use. Level 3, and that's the one that mostly just Tesla uses. Our plug-in hybrid will not handle level 3. You're talking about 125 kilowatts. That's a lot. And they're essentially always connected to a 3-phase service. And when you do that, that's going to draw 347 amps at 208 volts. Well, how many residential services will cover 347 amps in addition? It has to be a pretty big place. If you're at 460 volts, then it only draws 157 amps. So in general, that's not a residential option. You'll maybe see these out at a shopping center somewhere where Tesla has a big sign up saying, "Come and charge your Tesla here," and go in and shop at Burdines for a while or something while your car is charging. And according to the handwriting on the wall, folks are saying that in the future, higher charging levels are going to be available. So, charging levels. What do you get for a charging level? Well, how long does it take to charge? And again, the math is pretty straightforward. And right now, you get about 3 to 4 miles per kilowatt hour charge in your batteries, okay? And it depends how it's driven and whose vehicle exactly. So then we look at charging rates in kilowatt hours. And if we look at the level 1 charger with 1200 watt charging rate, that means 1.2 kilowatt hours are added every hour. And if you have 1.2 kilowatt hours and 4 miles per kilowatt hour, that means that in an hour's time, charging at 1200 watts, you get about 4.8 miles of driving. Okay, so if you drive an average of 25 miles a day, we're looking at roughly 5 hours of charging at night to recharge your batteries, which is our situation, and that's how we get our 500 miles per gallon with our plug-in hybrid. So it's essentially an electric vehicle, and the thing I worried mostly about is when the gasoline engine doesn't start very often, is there any problem with that? And then I realized that a lot of people leave their cars parked in our garage for 6 months on a trickle charger, come back and start them. So that seems not to be an issue. Although I did find out I had to change my oil after a year, even though the engine probably hadn't been on for more than a couple hundred miles. Anyway, rough estimate is that an hour of level 1 charging will gives you about 5 miles to the electric range. So in other words, you're charging at the rate of 5 miles an hour. Interesting way of defining charging rates. Level 2 charger, 5,000 watts. Well, that gives you about 20 miles per hour of charging. So if you're driving 100 miles a day, then you probably want to go level 2, because then you're charging 4 to 5 times faster, depending on what the charging rate is, somewhere between 3 and 7 kilowatt hours per hour. And level 3, in 1 hour's time, it'll dump in 125 kilowatt hours, which is 25 kilowatt hours more than the big Tesla will hold. And matter of fact, at this charging rate, normally the charging stops at 80%, because with lithium battery packs, you got to charge pretty slowly at the end of the charge cycle. So you make sure that you level off, the batteries cool off as you're charging towards the end. In any case, this is an answer to the complaint that it takes so long to fill your gas tank or your electric tank, which means we have to kind of rethink what it means. Rather than buying gas once a week or so, we just add electricity once a day or so, and life doesn't change a whole lot. And you have to buy your electric range according to your daily distance you travel. So anyway, this is where we stand in charging times. Let's look at chargers a little bit. Desirable features: they need to be compatible and they need to communicate. There's an app for your cell phone that you can ask your car what level of charging is at. If you've plugged it in and left it and sitting in a restaurant somewhere, you can check to see if your car is already charged, so you can ask for the check so you can move on. So charging time, it's a consideration. How much does it cost? Has to be safe, and it has to be code compliant. All right, that's where the engineers come in. And the architects come in by anticipating that there will be electric cars, and making sure there's provisions or the ability to add provisions for electric car charging wherever that car might be parked. Advanced is really neat. It would be bidirectional, adaptable, and portable. I find it fascinating to think of this particular scenario, and that is if you've got a 50 kilowatt hour battery pack in an electric vehicle, and you happen to be plugged into a charger, a bidirectional charger at work, and your car is fully charged because you got there at 8 in the morning or 9, and it's been charging as much as the utility is happy to charge it with. And it may well be that the utility is going to come on at 10 in the morning and say, hey, I see you're still charging, but if you are charging your car now, I'm going to have to charge you 16 cents a kilowatt hour instead of 13 cents a kilowatt hour to continue charging, or maybe 20 or whatever. And so the car will say, I've got 40 kilowatt hours now, so I'm okay. You can shut off. I don't need to pay the extra money. So that's like load management issue. Then, though, imagine at 4 o'clock in the afternoon, you've got all the electricity you need to get home or do whatever errands you're going to do, and you press some button in the car in the morning that anticipates how much you can sell to the utility. And at 4 in the afternoon, in comes a request from the utility that says, how about sending me 5,000 watts and 5 kilowatt hours over the next hour? And the car looks into the instructions it got from the driver that morning, says, yeah, we can do that, except what are you going to pay me? The utility comes back, how about 20 cents a kilowatt hour? The car says, well, how about 22 cents? You can probably imagine that conversation going on online between two Internet of Things creatures. And furthermore, this conversation is going to take place with the closing the deal in less than a second. And I find that absolutely fascinating. And we're going to see that. Watch for that. There's not much there now. There's some experimental setups out there. But over the next 5 years, watch for that one. It's a really interesting deal. The charger itself, you notice there's three big holes there. Those are the pins that have the ground and the current carrying, two current carrying conductors. The two small ones are your communication. When you plug that thing in, the car knows that it's plugged in. And if you try to start it up while you're plugged in, you can't go. It won't go anywhere because that communication that says, I'm plugged in. So you got to get out, unplug, and leave. And of course, those communication links, that's the ones that would go to the utility, and is where your information goes to the owner to be able to determine the level of charge in the car. Okay, I'm going maybe a little bit too slowly here, so let's go a little bit, speed it up a little bit. Electric vehicle battery types. Let's just talk a little bit. What is capacity? What is storage? Capacity is simply how many kilowatts can they deliver, how much power. All right, and they have to provide enough for maybe 30 to 50 horsepower. That could be 50 kilowatts for 50 horsepower. Well, maybe for a more efficient engine motor, 746 watts to the horsepower. So somewhere in the neighborhood of 50 kilowatts. And that's a discharge rate. And that's a pretty high rate. But you need that you need high power for starting a gasoline engine. So that's why we have 12-volt lead acid shallow discharge batteries in automobiles, because we need power to get them started. And then you don't need a whole lot of power anymore. But for starting it takes a lot of power. Storage refers to energy storage in kilowatt hours, and that's like in gallons of gas, okay? In other words, how far you can drive depends on how much energy you've got stored in your electricity tank or your batteries. And I have to keep in mind that driving electrics is like driving gasoline cars. If you have a lead foot, you're going to use more electricity, just like you're going to use more gas. And if you even slam on the brakes, the charging of the battery, you get more charging current, but you have to remember that there is internal resistance in the battery, and current going through that internal resistance dissipates power in the form of heat according to the square of the current, I squared R heating. So the faster you start or the faster you stop, you lose some efficiency when you do that. So just need to keep that in mind if you're driving. If you're concerned about efficiency, you want to drive, whether it's gasoline car or an electric car, you want to do the same thing. Okay, so lead acid versus lithium. Well, it says here lead acid is less expensive, and I'm not even sure that's true anymore. This was true maybe 2 years ago. But I've heard recently that lead acid can be bought, lead acid is typically around $200 a kilowatt hour of storage. And lithium now presumably can be purchased for somewhere in the neighborhood of $125 a kilowatt hour. So I don't know where or when, but I saw that number, and it may be. Lithium ion batteries have come down over the last 10 years by a very large factor, somewhere between 8 and 10. So they're getting less and less expensive. Lead acid, however, is not getting less expensive. So pretty soon lithium or some even more advanced battery technology may take over. I don't expect innovation to stop all of a sudden. I doubt anybody in the audience here expects any innovation to stop. So in any case, another nice thing about lithium-ion batteries is they don't give off any flammable gases when you're charging, so you don't have ventilation requirements. If you put in a lead acid battery charger in a garage, you got to be careful to follow the code on that. And there's a ventilation code. It's not in the National Electrical Code as such, but there is a ventilation requirement. And that's generally in the state building codes of how much ventilation you need in a garage if you are giving off hydrogen from a lead acid battery charging. So lithium ion has a lot of advantages over lead acid. Only one disadvantage is you have to make very sure you don't charge beyond 100% rating. And that means the charging circuitry is more complicated. If you don't charge all of the cells equally, then there's a problem. And lead acid doesn't have that same kind of problem. Sometimes you have a bad battery and they tell you one cell is dead, and of course in the lead acid all the cells are in series, so if you have one dead cell, you have one dead battery. Whereas in the lithium batteries, you got a lot of series parallel, so a dead cell doesn't necessarily hurt you so badly. So in any case, and the other advantage of lithium is they can be used for capacity or for storage. You can get kilowatt hours or kilowatts, and the reason simply because there's very low internal resistance in the lithium batteries compared to the lead acid batteries. Voltage converters, yeah, got to have those in cars because first you convert AC from high to low or from low to high with the transformer. And usually, and sometimes you just do isolation and keep it at the same voltage, but you want to isolate your secondary from your primary circuits of a transformer simply because then you can have two output wires, neither of which is grounded, even though one of the input wires might be grounded. So you can have a floating output, which sometimes is desirable. Again, with a transformer, an AC transformer, the power out is approximately equal to the power in. Good transformer has only about 2% losses, so you get 98% out compared to what you put in. You can input low voltage, output high voltage with the same transformer. It doesn't really care what you use as secondary or primary. So power flows can go in either direction through a typical transformer. DC voltage takes electronics to do that, but DC to DC converters are very common these days. And this is how the voltage in an electric vehicle or hybrid is converted up to that high voltage level to charge the high voltage traction batteries. So electric vehicles have DC to DC voltage converters, and sometimes the charging mechanism has AC to AC isolation in the form of a transformer. Here's the codes, folks. And this, of course, is what our life is all about as engineers and architects. Excuse me. National Electric Code Article 625 is on electric vehicles charging systems. NEMA has a whole bunch of standards. The National Electrical Manufacturers Association, they have 30 amp and 50 amp standards. The SAE J1772, that's the standard for the electric vehicle charging equipment. These NEMA are simply the plug-in socket connection options. But the SAE J1772, that's that thing that looked like a gas nozzle that you saw plugged into the electric vehicle picture previously. And with this J1772, we got the open charge point protocol, which allows chargers to talk to each other. For example, if you had only a limited service and you wanted 10 chargers on a service, maybe they can't all be on at the same time, so it allows for some load management. Underwriters Laboratories 2202 is the standard for the electric vehicle charging system. And you can buy one for a mere $1,000 if you're interested in what 2202 has to say. And 2231 is the standard for personnel protection systems for EV supply circuits. Because electric voltage supply circuits can be fairly high current, and so you need to make sure that the personnel who work on these are properly protected. So these are the standards you can look up if you want to get into the EV charging business. Let's take a look at some of the chargers. One on the left is a level 1 charger, and that's the J1772 connector that we just talked about. They all have that same pin configuration. And there's a level 2 charger outside a car dealer. And here's a level 2 charger that connects up in a garage. And you notice the antennas there for probably it has a Wi-Fi connection, or it could even be a cell phone type connection. So moving along, let's say we want to add a charger. We have to determine whether the service of the existing building can handle that. So NEC 220.83 is the, or 220.84, depending whether you're single family or existing multifamily, existing single family. And for other sites, there are other sections of the National Electrical Code that apply. Now 220.83, let's do an example for that. 1,500 square foot dwelling, no new air conditioning or heat, just the new charger. Will it work? All right, well, let's do the load calculation here. Air conditioning, 3,600 volt amperes. General lighting, 4,500. Washer, dryer, refrigerator, 5 appliance circuits. Electric water heater, electric range, 5.5 kW level 2 charger. Notice that you just add your new 5.5 kW level 2 charger in with your water heater range and other appliances. That's basically considered an appliance. And then we do the existing dwelling, adding a load calculation. The first 8 kVA at 100% gives you 8,000. And the remaining, you take at 40%, and that's 15,240 volt amps. So if you have 120 240 volt service, that means your new, with your new 5.5 kW level 2 charger, your load calculation is 96.8 amps. So even if you had 100 amp service, it would work. But there aren't an awful lot of 100 amp services out there anymore. It's probably more common that you're going to have 150 amp service. So almost always, you're not going to have to change the service in order to install a level 2 charger. There may be some case, and obviously you have to do a calculation to find out. The important thing, of course, if you look in the lower right-hand corner there, there may not be room in the main distribution panel for a 2-pole 30 amp circuit breaker or a 2-pole 40 amp circuit breaker. This happens to be a 5.5 kW level 2 charger at 240 volts. So, do I have a typo here? Well, let's say a 2-pole 40 amp circuit breaker. Not a bad idea to wire it with 2-pole 40 and number 8 anyway, because you can always use less. And if you decided you wanted to buy a bigger one that has a bigger 7 kW charger, then you'd be ready for it. So, but then again, it's not unusual, done all the time when adding air conditioners. People used to tap right at the main service. Let's see, I hear ding dongs. Let's see, it looks like we still have the same number of participants. I haven't seen any messages. pretty soon we'll maybe just take a break and say, okay, well, let's say at 11 o'clock, we got 9 minutes. We'll take a look at anybody wants to discuss anything we've covered up to this point, but feel free to type in something sooner than that if you like. So, okay. So the service calculation is not that big of a deal for a single family dwelling, and this of course also applies to an installation in a multifamily dwelling. The only thing you'd want to watch out for is if you're multifamily and all of a sudden they want to do one for every single person, every single occupancy, then you might want to pay some attention to whether there's a big enough service coming into the building to feed the distribution network for all the different individual meters. So you might have to do a separate calculation for the main service coming in from the utility as well. With one, it's not going to make much difference. And the other interesting thing is, and one reason for maybe not even using this method, is that most buildings are now a lot more efficient than they used to be because the owners themselves have tended to move into LED lighting and more efficient refrigeration. The only change there is when you put that huge big screen TV in, that might be a little bit more than usual. But in general, for 150 amp service, it's probably that turning everything on won't result in much more than 100 amps in that being drawn. But of course, the alternate method is to actually look at what the maximum peak demand has been. But you know, measuring maximum peak demand over 12 months, that's a 12-month process to do that, and that takes a long time. Residents, they don't have demand meters, they've just got plain old energy meters. So the first, the 22087 does allow an analysis based on maximum peak demand over the past 12 months. But that also allows you to measure the demand for a month, provided that it's the month that you use a maximum amount of electricity. And you also have to monitor both of the line currents. But with some of the home automation systems now, this is not a major effort to throw in some current transformers in the distribution panel, and at some point use them maybe for some load management anyway. Anyway, if you have that monthly demand, then you add the new load to 125% of the maximum monthly demand, and then you can compare it with that calculation you did in NEC 220.83, and you can take the lower of the two. So if somebody has really paid a lot of attention to energy efficiency and installed super efficient air conditioning, and super efficient lighting, and maybe even has either a solar water heater or a water heating heat pump water heater, their energy use is going to be a whole lot less than it may have been calculated to be 20 or 25 years ago. So just something to keep in mind for the folks who do these kind of calculations. Where do you tie in an electric vehicle branch circuit? Well, if you have a breaker space, you put it in the main distribution panel. If you can't put it in the main panel, and if the main disconnect is actually closer to where you propose to locate the charger, then you can tap in using the tap rules in the National Electrical Code and tap in anywhere along the feeder between the meter and the main distribution panel. Probably can't practically do that because the feeder is probably going to be in conduit, but not necessarily. So depending on exactly how that feeder comes in from the main distribution panel to the from the meter to the main distribution panel. So you can use your rules for tap distance, the 25-foot rule, 10-foot rule, depending, 25-foot tap requires larger wire size. In any case, NEC 240.21b2 is there. And all you need to do is make sure the charger branch circuit over current protection, if it's within 25 feet of tap, as long as the conductor ampacity to the mains overcurrent protection is at least 33%. All right, so in almost every case this works because the ampacity of number 8 is 55 amps, and that means you can have a 175 amp main and have a 25-foot tap. And if you have number 6 wire and a 25-foot tap, then you can do that with a main disconnect up to 225 amps. So this is for the 25-foot tap. If you use a 10-foot tap, then the wire sizes can be smaller. And so it's just a matter of where can you use a 10-foot rule and the 25-foot rule. But there's a reasonable likelihood that it may be desirable to tie in an electric vehicle charging branch circuit somewhere other than the main distribution panel. Here's this is my building, okay, and this is what I was going to do if necessary to connect in a level 2 charger. You see the meter center there, and you can see all the gutters that feed the feeders up to the distribution panels and the units above. And it's an easy 25-foot run, less than 20 feet, to tap into that gutter, or tap in at the meter and run your number 8s through the gutter down to a disconnect for the EV. And then if the garage is on the other side of the wall of those meters, then you find your way through that garage wall over to the vehicle and you've got your charger. So this is just happens to be something that would work for the building I live in, and it's the sort of thing you're going to look for if somebody in a condominium calls you and said, hey, I want to buy a new Tesla, or I want some kind of electric vehicle. You get the data on the charging, you run your calculation, and they plug in their vehicle when they bring it home. So NEC 625 talks about electric vehicle charging stations. All right, and so again, it's a part of the NEC to pay attention to. It's got all the rules. Fastened in place, it simply means you can't remove the charger without a tool. You can have a charger that is fixed in place. In that case, you need a tool to remove it. Well, in my case, I need a screwdriver to unscrew my charger from the mount that I put 18 inches above the floor to follow that code requirement. And if I wanted to take it with me on a trip somewhere, I'd have to take a couple screws out to take the charger along to wherever else it might be used. Nominal AC voltages are defined. DC voltages are allowed up to 1,000 volts. So in other words, the charging voltage you use to charge your vehicle is pretty low. It's almost anything available, and some things that aren't available in a residential situation, but only in a commercial or industrial situation. 625.5 talks about electric vehicle supply equipment, VSE. And there's work going on with wireless power transfer equipment where you put induction coils under the car. That's the wireless, WPTE is wireless power transfer equipment. I have not seen any of this. It must be out there or it wouldn't be in the code. Maybe just thinking about it, it's hard for me to imagine the same kind of charging that I do on my electric toothbrush charging up my electric car, because everybody knows magnetic circuits, if you've got too much of an air gap, you have a lot of losses. So this is something I'd like to follow up on personally a little more to see exactly what kind of efficiency they get. But it's something that's out there, and after all, the title of this is essentially predicting what's going on in the future. So the National Electrical Code is very much into electric vehicle charging. It's about 11. Does anybody have anything they want to practice typing with to make sure your fingers can still move, whatever? Are we doing okay here? Are you picking up any useful information? Comments would be very welcome, because this is the first time we've done this particular webinar, and any feedback we can get that might improve it, we welcome your comment. It's okay if you like it too. You can even tell us that. All right, so don't hesitate to type in a message if you're thinking about whatever. Here's more NEC 625. And again, this is stuff you can read as long as you know where to look for it. All right, 625.48 in particular covers interactive systems with references to a bunch of other sections, 702 and 705. 705 and UL 1741 are the systems that apply to wind and photovoltaics, tying into the grid. So if, in fact, you're having a bidirectional system or interactive, they also have to comply with NEC 702 and 705. So it's another ballgame to be selling back to the utility. You need to pay attention to that as well. Of course, if you install a Powerwall, which we're going to be talking about in a little while, that UL 705. Sorry, the NEC 705 applies to that. And important thing here is the 625.50. Your charger has to be more than 18 inches above the floor. And that's the same old rule about if there's, who knows what might be in a garage gasoline near the floor, gasoline fumes. And if you unplug it and there's a spark, and all of a sudden all that gasoline explodes. So the general rule is any outlet in the garage has to be more than 18 inches above the floor, just for that main reason. Then again, if you want to wash the floor, you keep water out of it as well. Okay. And a little more. NEC 625, again, you pretty much want to read that whole section if you're going to install an electric car charger, just so that you're aware of what's there. And if you have an electric truck, NEC 626 covers that. So there's the two possible charger configurations. And that simply shows that there's a little more stuff on the bidirectional charger than on the one-way charger. And once again, a reminder, you can get copies of these slides, PDF copy, if you want to study them or look at them more carefully after the webinar is over. A simple email or go to the website, and they'll take care of that for you. So that's it for the electric vehicle part of the program. Let's now talk about home automation. A lot of it out there, and the interesting thing here is with home automation, they sell it everywhere. It's at Office Depot, it's at Home Depot, it's hard to imagine an architect or an engineer or a contractor getting involved in helping somebody else with a home automation system, except for the fact that not everybody wants to take a chance on guessing right as to what's the right thing to buy, because there's a lot of stuff out there. So what I want to do here in this session is take a look at some of the communication protocols, some of the stuff that should be used in making decisions about what kind of home automation would be the most useful in a particular home environment. Actually, yeah, NEC 2017 is the one reference, Robert, and NEC 2020, a lot of jurisdictions haven't adopted the 2020 NEC yet, but I have a copy of that sitting. In fact, I did a comparison of 2020 to 2017 for a different web course. And there's a little bit more information on all these things, but the one I'm referencing for this is a 2017 because this was put together before the 2020 was available. So yeah, I'm glad you point that out. Thank you for that. I really should take a look at the 2020 and see what the difference is. The point here, though, was just to kind of predict the future so that people would recognize that this is something that when the 2020 code comes out, you want to make sure that there are no major changes. So, okay, let's look at some of this stuff here. What's a smart home? Well, it has to have an IQ of more than 80, I suppose. I don't know. Well, it's got a bunch of stuff in it, for one thing, all kinds of heating, air conditioning, television, camera systems, who knows what. But anyway, here's a definition for you from the people at Smart Home USA, and you can go to their website for more interesting things. By the way, most of the references here are on the bottoms of the slides. I haven't mentioned them, but they're Richard, welcome to the second half. So here's your definition. And basically it simply means if things can be controlled remotely, and also if they can be programmed to do things, there's almost the distinction between smart and kind of smart is almost like the distinction between a hybrid and a plug-in hybrid. Do you consider a programmable thermostat to be a smart thermostat? Not normally, because that's just a one-way thing, programmable. A smart thermostat would be one that recognizes people in a room, and therefore it cools it down a little bit, and it recognizes when people leave the room, and then it warms it up a little bit, or whatever. It may be programmed on what it should do when people enter or leave the room. But smart tends to imply that it can make some decisions by itself, maybe within limits or parameters defined by the owner. All right, guess what? If you look in the NEC, and this includes 2020, you go to the index, look for smart homes or home automation, it isn't there. Okay? So therefore, a lot of devices are going by the owners. I don't know, we've got lots of I have a lot of people in my building who come down for the season and then they go back to north for the summer, and they've got smart thermostats and cameras and stuff so they can keep an eye on their place. And it's kind of handy to have a smart thermostat that you can dial up on your cell phone and determine what the actual temperature is and what the temperature set point is, and that gives you a pretty good idea whether the air conditioning is working. Doesn't necessarily tell you whether the condensate drain is clogged and your overflow pan is flooding your wherever that might be located. But you'd have to depend on a smart water detector to give you that information, maybe. On the other hand, if your air conditioner has a float in the condensate pan or other kind of a sensor that shuts down the air conditioner because the condensate drain is plugged, then you're going to know that something is wrong with the air conditioner because your set point temperature is different from the actual temperature. So it's either going to be colder or warmer depending on the season of the year. More than likely, though, if you're talking about condensate drains, it's going to be warmer in the dwelling space than the set point. So you call somebody to get them in there to fix it. Very simple. Now, there are some things where smart devices are covered, like in an energy management system. There's certain things you're just not allowed to turn off in NEC 750. And 760 applies to fire alarm systems. And yeah, you got to be careful of fire alarm systems. You don't put them on a load management basis. They've got to run all the time. And same with communication systems. So you need to look for rules in 750, 760, and 800, even though smart homes specifically and home automation are not addressed in the code. So how do these devices talk to each other? Well, some communicate with wires, like power line carrier circuits. Some are wireless. Some are on house power, some are battery operated. Other run on house power with battery backup power. Pretty typical for smoke alarms to have a backup battery in case power is lost, if utility power is lost. And there are at least 15 different communication protocols on the market, and some are compatible with each other, some aren't. And so if you start mixing and matching your various smart devices, they may or may not be willing to talk to each other, and they may or may not need to talk to each other. Maybe your smart lawn watering thing doesn't have to talk to the thing that controls your lights or your TV set. So, but they're decisions you got to think about if you want to get it right. So the key is system compatible and reliable, and the protocol might make a difference there. So given that they're important, we should take a look at them. X10, it's the oldest one. Some of you, I don't know how old you guys are. I happen to be 76, and I can remember when Radio Shack first came out with a little box that I could plug in next to and then put on my nightstand, and I could turn on a light out in the living room or in the family room. It was plugged into the wall if I heard a noise. And I use X10 communication. The central control box plugged into the wall, radio frequency signal coming out on power line carrier, power lines at 60 hertz, the RF signal somewhere in the 100 kilohertz range, so it rides right on top of the power line signal. If it gets to the transformer feeding the building, the transformer acts as a filter. It can't get past that, so you can't control your neighbor's lights unless they're on the secondary side of that transformer, but hopefully the attenuation, they drop out. The receiving devices have an address. Just like when you press your garage door opener, it only opens your garage door. You press your TV control, it's designed to work with your TV, although there are some universal remotes, but they all have their encoding so that they only work where they're supposed to. All right, and most of the commands were just on-off. Turn the lights on, turn the lights off, although sometimes you had dimmer options. But you couldn't control very many devices with this particular X10 protocol, but it got things started. Here's a picture of how the X10 works. You have these bursts called pulse code modulation, I guess, because you're pulsing this high frequency thing and it rides on top of the sine wave. And X10 is a relatively low amplitude, 4 volt signal, somewhere in the 300 kilohertz range, just below the AM radio broadcast. And wow, it could control up to 4 devices. And that was really something 40 years ago, 35, whenever it came out. I don't remember exactly, but it's been around for a while. The UPB signal, that's a little different. It takes into account the shortcomings of the X10, but it's still a power line. It still controls through the power line by putting a high frequency signal on the power line. But the UPB has, that's the Universal Power Line Bus, I think that stands for. It's 40 volts instead of 4, so 10 times as big as what we see above for the X10. And the UPB can control up to 64,000 device addresses, and it's also 30 times faster than X10. I don't have 64,000 devices in my house, so clearly this could be used in a huge factor, a huge something or other, because that's an awful lot of devices. So it gives it a lot of flexibility. But then again, you need the power line connection to whatever you want to control. And that won't work very well on a doorbell, or won't work very well on a number of things, like a thermostat that's running on 24 volts AC. The 120 volt to 24 volt transformer supplying power forgive me, sometimes I have to drink water to clear my throat. The 120 volt or 240 volt to 24 volt transformer to the air conditioning thermostat, that's going to cut out any signal that might go to the thermostat unless it has bypass filters or bypass capacitors to do that. So in any case, the control signal is isolated from the power line by a high pass filter. It means it only lets the control signal through. It does not let that low frequency signal. So you get a series of bursts of this 300 kilohertz signal. And I made these all the same length, but you can change the length of them, or you can change the spacing, and that's how you do your encoding. And it's just kind of that straightforward. Okay, so that takes care of how you do the power line carrier stuff. Z-Wave protocol is very popular. There's more than 250 Z-Wave Alliance companies. These are people who have said, all right, let's make our products compatible. Let's adopt some standards. All right, so great. There's now more than 1,200 products certified by the Z-Wave Alliance that they'll talk to each other. This is a two-way wireless protocol, operates in 900 megahertz band. The devices run on batteries. They talk to each other. And what that means is one device can pass along a message to another device. And you can have 232 devices on this system. So that conceivably could be within a condominium environment where all of the fire alarms could be on that, water alarms could be on it, any other thing that you might want somebody at a central monitoring station to know that something is going wrong in one of the units. Whether it's fire, smoke, or water, those are the three things that any condominium dweller dreads is the alarm going off for any of that stuff. But it does happen. You just need to look out on the street and see how many water cleanup companies there are and mold remediation companies. So in any case, the Z-Wave protocol is lower power than Wi-Fi, which is also used a lot. But then it's also a longer range than Bluetooth, which is a hint that Bluetooth is also a possibility. And the other thing is it's easy to install. And because of the alliance between many manufacturers, as long as you verify that you're working on Z-Wave, you can connect devices of different manufacturers who are part of this alliance. So let's take a look at how this works here. Let's say we've got 14 devices connected up. One thing the Z-Wave system needs is a centralized hub that passes out the instructions to everybody. And notice if the hub wants to talk to device number 6 over there, it's probably going to talk to it by way of device number 1. So device number 1 sees a message coming along. It sees that it has the address of device number 6, so it just passes along to device number 6 and doesn't even bother to read it. It doesn't care. It's not for it. Totally different from NSA and all of other security intelligence folks here who like to listen in on our conversations. I don't know if they're listening in on this program or not, but the Z-Wave guys, they're pretty nice. They just pass along information to each other. If you have a problem, let's say device number 4 there, the one with the big blue X in the middle of it, let's say that the battery runs dead on that, and device number 14 wants to, which normally is communicating with the hub by way of device number 4, now device number 14 wants to get a message to the hub, so it addresses the hub, says, hey, I'm detecting a water leak, or I've got a problem with the thermostat. So it sends it to the hub by way of device 13, 12, 3, and 3. So it can talk around 4, and it still gets to the hub. It's allowed up to 4 different devices to go through, so it could go actually from 14 to 13, 12, 11, and 3. But if 3 is not on, then, well, then we need to look what's the likelihood that 3 and 4 both go down. And there's just, these are wireless, so there's obviously a maximum distance these things can be separated by. So there's an advantage. The more you have, the less the distance separation and the more reliability you have in being able to communicate with the hub, which then in turn can connect to the internet. And once you're there, you can go wherever you want. Some of the blue boxes on the right here, separation depends on the device series. The 700 series allows you 328 feet between devices. That's a lot. So, and the hub itself has a network ID, so that isolates us from other systems. Any instruction comes in from the internet has to go to the address of that particular hub. And obviously, if we're connecting to the internet, security is an interesting thing. We're not here to talk about security. We're just here to talk about kind of how they work. But anytime we get into the Internet of Things, there's oftentimes concern over security, so it's a question to ask. Okay. Other protocols. Zigbee. What's that? Well, it's another protocol, but it's wireless home automation protocol, very similar to Z-Wave. It works best, though, if all the devices are from one manufacturer, as opposed to Z-Wave, where you can mix and match. They don't have the same alliance. But it's low cost, low power, it has good range, and it works pretty fast in the mesh. So Zigbee is, it's okay. You just need to know what its limits are. It's wireless, though, so that makes it attractive for broadcasting for thermostats and things like that don't work well with a wired connection. And normally, if you don't go with power line carrier wiring these days, you want wireless. You don't run these long cables of 18.5 or something like that, or like for a thermostat. Yeah, you still have a wired connection from a thermostat to an air conditioner usually, but even that now is becoming wireless with the thermostat control. You can have just like a remote for the TV or a remote for a ceiling fan and so forth. The main thing is I kind of like stuff to be fastened to the wall because I don't lose them that way. And I usually can remember where they are. And Ocean, another wireless protocol. This uses so-called frequency shift keying modulation of the primary frequency, which simply means that you're starting out at a certain frequency and the encoding is done by moving that frequency up or down by a certain amount. And that's been around for many, many years. That was around 65 years ago when I was a ham radio. No, not 65, 64 years ago. Well, it was around before 64 years ago as a communication that kind of followed along the lines of Morse code, but it's a lot faster and a little more automated. Anyway, Ocean is basically designed to improve performance of systems. Insteon, another one. That works power line and wireless. So you can have multiple message pathways. And the fact that it's compatible with an X10 network is useful. So, and like we mentioned earlier, there's at least 15 of these, including Thread, Bluetooth, KNX. And again, if you're interested in these things, order up the PDFs for the course, and then you can read it a little quicker. Or you can actually just download them from the website, I think. So that's all right, too. Smart thermostats. Boy, there are a lot of choices here. Even with what I know about smart thermostats and my air conditioning, and I'm reasonably competent on air conditioning, even though I'm an electrical engineer. Yeah, I'm not sure. I mean, we've got a heat pump, so I got to be able to have heat and cool both. I've got to have a lot of stuff. It's in a reverse cycle system, so I need to have the right number of contacts to reverse the cycle and tell it heat or tell it cool. It's not a resistive heating. I've only got a single zone, but what if I had more than one zone? My system only has one stage, but now there are multiple stage super efficient air conditioners out there, including inverter type air conditioners that don't have multiple compressors. They have one, but you vary the speed on it, and it gives you exactly, it keeps your temperature, your room temperature exactly on the button rather than bouncing back and forth. Do you want to switch automatically or manually between heat and cool? What kind of a fan have you got? What about your compressor? Any variable speed stuff in the system? Do you want to monitor the performance? Do you want to monitor failures? Do you want remote control as well? Smart thermostat, more than likely you're going to want remote control, but if it does a lot of those other things, those are things you want to know even if you're home. You want to tie in with peak load or energy management so that you can reduce your electric bill by letting the utility control your air conditioner. You could have a humidity sensor, occupancy sensor, voice recognition, all that kind of stuff. It's all out there. And probably, well, maybe you might even want it compatible with one of your existing systems. So, smart thermostat. I wouldn't take it lightly and just go out and buy one. I'd want to think about it for a while. I haven't bought one because we live here most of the year round and have pretty much daily check on what's going on. But I'm sure that I'll break down one day and decide to invest in one of these fancy thermostats. Then there's lighting control. You can get plug-in modules. You can have wall switches. You can have a switch that you lift up off the wall. They're small, easy to lose. As I mentioned before about remote controls, how many times you misplace those things. They're easy to use, but also easy to use sometimes means easy to lose. Wireless or wired, manual or automatic. Hue control. And that's interesting, isn't it? If you've got LEDs, you can switch that light from red through a whole spectrum of different colors. Now, by just varying your hue control. I'd be interested, as we go through some of these things, I'm interested in the extent of adoption, and I would really appreciate if some of you would just type in and tell me if you've got any of these things or what you happen to have. You might be concentrating on listening now, but at some point we'll take a little break, and I want to kind of finish up by hopefully 5 minutes to 12, so that we can then maybe do a little survey of how many people have various smart home devices. Irrigation control can save an awful lot of water, and one of the more popular likes to communicate via Wi-Fi. And what is smart irrigation control? It's not just a matter of measuring whether the grass is already wet, because if it's cooler outside, the grass doesn't need as much water. And this soil type makes a difference how fast the water soaks in. What kind of grass is it? How much shading is there? You don't need as much rain or much sprinkling when it's shade. So that's smart, and it's out there. And it likes to communicate via Wi-Fi. So if you're doing Wi-Fi, if you've got a router, you want to make sure that router is within communication distance of your irrigation control, or you want to extend that or something. Let me check here. Yeah, okay. Oh, how far down did I go? I made a mistake. I shouldn't have done that. Excuse me, folks. All right, I think we're on number 42. Yeah. Okay. Controlling appliances. Again, not particularly new, but how many times have you left home and wondered whether they turned off the electric range or the light in the wherever? Well, you just ask your phone if you turned off the light. You don't have to run back upstairs and unlock the door and run in and see if the kitchen's on fire. You ask your phone. Or maybe you've got a surveillance camera and you ask your phone to turn it off. It'd be nice to have a refrigerator when you're away on vacation. One of the really bad things is if the refrigerator's turned off. It happened to me many years ago, almost 50 years ago. Cleaned out the refrigerator, put everything back in, left for Minnesota for Christmas, came back home, realized we'd forgotten to turn the refrigerator back on again. And we couldn't. It was in an apartment. And I didn't want to tell anybody about it. So you're the first people to know about this. I took the refrigerator apart and pulled all of the fiberglass insulation out and replaced it. And boy, it would have been nice to just know the refrigerator turned off. I don't have that in my house now either now, but the neighbor across the hall has it. Water heater tracking energy usage and tells you that something's weird. Leaky faucet, for example. Overflow valve, pressure relief valve going bad. That's a pretty nice feature to have. So yeah, there's very interesting stuff out there for appliance control and so forth. Um, Security cameras, another major kind of a decision to make. And here's just a few of the considerations for the design. Um, I'm not going to go through them all. I'm just going to let you read them quickly. But you can see that between A and B, A has an awful lot of redundancy, and B has almost no redundancy. If your recorder goes bad, then you may not be able to get information from any of the cameras to either of the monitors. So it really is depending on that recorder, whereas the system in A, you're going straight from the camera to the monitor. Each camera has three connections, one to the recorder, one to one of the monitors, and one to the other monitor. Whole lot more wires or a whole lot more wireless, depending on how you do it. But there's a lot of considerations there. So suffice it to say that read this slide before you run out to buy it, if you haven't done so already, and it'll give you a little direction where to look. Cameras, at least 7 different formats on cameras, different resolution. The more resolution you've got, the more bandwidth you need, the more power you'll need. So there's a lot of compromises here. Sometimes the higher resolution reduces the frame rate from 30 frames per second to 20 frames per second. Mostly that's okay. You just want to see whether something is moving, and every 20th of a second you get a new take on that. So that's certainly going to give the information you need. So again, formats. What do we got? MJPEG, MPEG-4. I can never remember what JPEG means. It's the converting files to JPEG. It's a compression formula in any case. And the thing is, there are interesting ways of minimizing the amount of video data and still getting the information you need. As you probably are well aware, if you have a video camera, the video on your phone, a 1-minute video is taking up a lot of memory space. So unless you've got some kind of compression or data compression, if you want to have 24 hours worth of video and record it in some reasonable thing, you want to compress. And normally you record a frame, and then the next frame, if there's nothing different, then you just put a quick code, say it's same as the last one, and same as the last, until then you just look at things that change. So these compression formats, the one that has the most compression is the H.264, and the reason for that is because it compresses the same amount as the MPEG-4, but it also compresses the initial frame of a sequence, which MPEG-4 doesn't do. And again, what does that mean? For the moment, we're going to leave it at that and move on, because time continues to move on. That's one of those things we have a lot of trouble stopping. More desirable camera features. Wide dynamic range. Oh my gosh, yes. What if you're taking a picture inside a room when the sun is shining into the window? You've got that huge contrast, and it's a very clever way to do that. They stop it down to block out the light and take a picture, and then they take a picture of what's there, and then they combine the 2 frames so that you can take care of the high contrast. Twice the amount of data, but maybe worth it to see the whole picture. Do you want to store data locally in the camera? It means camera's going to have a little bit more memory. It's just like your printer now has lots of memory. Printers didn't used to have lots of memory. They had to depend on the memory of the computer. But then when memory got cheap, you start putting it all over the place. Illumination power, that means that's not going to be illumination power more than likely that's going to be cabled so you have a power source, whether it's infrared or visible. Again, consideration that we need to be thinking about. All right, smart door locks. Again, something to think about. Demand control. Now here, let's talk a little bit about demand control because it's been around for a long time. I can remember many years ago, the utility, we signed a contract telling the utility, you can control when our water heater is on and when our air conditioner is on. Many of you might have similar. Okay? And when you've got demand control, it means utility simply controls a certain number of kilowatts of load so that it helps them through their peak loading in the afternoon situation. So the occupancy control now, if it gets smarter, it can actually have that conversation about payments with the utility, as we were talking about with the electric vehicle charging. So demand control can be implemented in a number of different ways, and usually there's a control box tied into a hub that goes to the utility. That's the usual situation. Energy management system, NEC 750, says it is a system consisting of any of the following. My goodness, I ran two words together. This is the first time I've noticed it. Monitors, communications equipment, controllers, timers, other devices, and so forth. And if you go to NEC 750.20, it says you do not try to do energy management on the following loads: fire pumps, healthcare, emergency systems, legally required standby, and critical operations power systems. All right, so yeah, it's pretty obvious. It makes sense, but if somebody says, I want to do it, and then at least you've got a code reference that says, hey, I can't do that. So NEC 750 if you want to do energy management. And 750.30a prohibits overriding load shedding controls that are associated with 750.20. Okay, so you can't override the load shedding in order to load shed if it tells it to shed. Okay, so there are a lot of myths, though, about energy management that we'll come to. Obviously, we don't want to put energy management, all of a sudden the elevator shuts down for 5 minutes while you're stuck on it. No, you don't do that. And you have positive mechanical ventilation in hazardous locations. No, you don't want to shut that off. Exhausting hazardous gases or whatever. So yeah, there's logical stuff you don't turn off, and National Electrical Code 750 tells you about it. There's some myths on energy management. Some people believe timers on electric water heaters save lots of energy. The only way they can do that is if they force you to use less hot water. The other way you can save more energy on an electric water heater is simply to turn down the temperature of the thermostat on the water heater. Most dishwashers have booster heaters if you want to use them. And most other things, they don't use the water at full heat anyway. They mix some cold water in with it. So you just add a little extra cold and less. And what you save on this is in tank losses. If your temperature of your water, plus if you don't need to wash your certain things at a certain temperature anyway. Replacing the water heaters with tankless water heaters saves lots of money. Well, not necessarily, because if the tankless water is in the same place that the regular electric water heater is, most of your losses are in the piping between the water heater and the faucet. And you can figure that out really easily by simply, when you shower, find your outlet, your hot water outlet that's furthest away from your water tank, put a pail under it, turn it on, and see how much water runs before it gets hot. Because all that water in your pail used to be hot water. It just cooled down in the pipe. And then you can figure out how much it's worth, because you can do that calculation. And we're not going to do that in this particular webinar, but there are others one can sign up for to do that calculation if you haven't done it before. Most good engineers, architects can figure that out. There's been a myth that swimming pool pumps need to run continuously. Not so. Anything a pump can filter will sink to the bottom in 10 minutes. The only reason to run a pump continuously is if you're heating or if you are adding chemicals and you can't change the rate of adding chemicals. So there are things written on swimming pool pumps that dispel a lot of these myths. If you want any of that information, ask for that when you send your email to PDH, and I will provide him with that information that he can share with you. Surge suppressors, they don't save energy. They might save equipment, but they don't save energy because energy is power times time. And if you have a surge that lasts a millisecond or less, there's not any energy associated with that, just power and the capacity to do destruction. Power factor correction capacitors. Sorry, they save energy on the line up to the power factor corrector, but nothing downstream from the power factor corrector. I proved that to an electrical inspector once, and he was very pleased to see it proved conclusively that they do not save energy on the load side of the power factor correction capacitor. And lighting dimmers don't save energy. That used to be the case 50 years ago, but now they save lots of energy if you dim your lights. So here's some facts. Again, you can read those. And mostly to save energy, you buy efficient equipment. The energy management is not nearly as important as the efficient equipment unless it turns things off when you forget to turn them off when you're away, and helps you reduce the runtime. All right, so interesting facts and fiction. By the way, facts and fiction stuff resulted from a research project that we did at my university way back in the early 1980s. So now let's look at Powerwalls. We've got a full 5 or 10 minutes left, and depending on how much discussion we want to have. What does a Powerwall do? Well, they're just small energy storage systems. They've been around for a long time. Powerwalls are not, but small energy storage systems have. And there's lots of photovoltaic systems that have been developed that include battery storage. A standalone system, you know, if you're off the grid, you have to have battery storage. DC coupled grid connected systems and AC coupled grid connected systems are two types of energy storage type systems that we're not going to get into today exactly what they are, but there are other sources of information on these systems. They're a little complicated. They require some on-site programming. So mostly what people have is this particular configuration. You got power coming in from the utility, power goes to the main disconnect, it goes to the main distribution panel, and that's it. So then along comes the Powerwall. And now we can do the following, and that's a little more interesting. We take a look at this. We have utility feeding a main disconnect, but this has feed-through lugs on it. And the feed-through lugs happen to feed the main distribution panel with an automatic relay. And the reason for this is if you lose the utility, this automatic relay has to disconnect your main distribution panel with uninterruptible loads from the interruptible loads in the main disconnect with feed-through lugs, okay? So you add this combiner panel and you buy a Powerwall. Forget about the PV for the moment, but the Powerwall is there. When the utility is on, those are normally closed contacts, and it charges up the Powerwall. And when the utility is off, goes off, then the Powerwall recognizes that. It's a built-in rectifier to charge batteries, a built-in inverter in the Powerwall to dump AC into the combiner panel, which is then used with the uninterruptible loads in the main distribution panel with the main circuit breaker. All right, so the Powerwall gives you power backup, but the other thing a Powerwall gives you is the possibility of getting onto a time of use rate with the utility, so that when your demand is going up in the afternoon, or when utility demand is going up in the afternoon, you can engage your Powerwall that's been all charged up with nighttime power and say, okay, I want to use you for the afternoon now, and disconnect from the utility. And I've got to deal with the utility for time of use rates, so therefore, or maybe I'm just going to use this Powerwall to dump power into the system so that the utility doesn't supply me as much, because remember, we have these interruptible loads, which might be, you know, something like an air conditioner, water heater, dryer, you know, heavy power, high power loads, maybe even electric vehicle charger. So I think you can see the picture. Then you add photovoltaics. The photovoltaics runs into an inverter. The inverter goes into that combiner panel. And it can charge up the Powerwall now. So if you lose your utility and that automatic relay contacts go open, you've got a standalone system now with your photovoltaic array, inverter, combiner panel, uninterruptible loads in your main distribution panel, and your Powerwall is now your energy storage system. So it's serving a multi-purpose. So again, the explanation is in the blue box with the white print in the lower left. And that's basically what we just talked about. There's obviously, when you're on your own, you've got a situation here that your PV has to make all the energy you need day and night, and if it doesn't, then there has to be some load management going on, because the Powerwall has to supply everything if there's no utility and no sun. The bottom line in the blue box there. But it's interesting to be able to do that, for sure. So how do you size the PV and the storage? Well, again, you need your maximum daily total load, and you get that from your maximum monthly kilowatt hour bill. So if you got 1,200 kilowatt hours, divide by 30, and this isn't really a maximum daily total load of 40, it's really more of an average of 40. Okay, on the other hand, it's a maximum based on the maximum monthly. So on that maximum month, you're averaging 40, all right? So then you have to decide, okay, how much of this 40 kilowatt hours do we really need? So you need to kind of go through your loads, and in this particular case, more than likely the air conditioning and the dryer and the hot water are going to use at least 20. So that means all your other loads are using about 20 kilowatt hours a day. And so you want to make 20 kilowatt hours a day with photovoltaics? Well, you can do that. There's lots of nice programs that tell you how much electricity you need, but on average, you'll make about 1,500 kilowatt hours a year for every kilowatt of photovoltaics you've installed. And so if you want 20 kilowatt hours a day, you need about a 5,000 watt photovoltaic array. And that's very typical for residential. And that's going to cost around $15,000. It's going to give you an amortized LCOE, levelized cost of energy, of about 6 cents a kilowatt hour. And that's pretty cheap, because you're talking about paying for that thing over a 25-year life of the system, and 25 years it's probably going to last longer than that. This NREL-SAM, if you want to Google NREL-SAM, that's a free calculator provided by the National Renewable Energy Labs. So wouldn't it be nice if you make 20 kilowatt hours a day, then maybe store 20 of those, or at least maybe 15, because maybe some, if you're making them with PV, they'll use during the day, so you won't be stored. So here's your Powerwall. And if you got about 20 kilowatt hours of usable storage, even if you have 10, you're doing pretty well. And most of them are somewhere around 15, 16 kilowatt hours, I think now. But then you can buy more than one if you need more than that. So, last slide. What does it do to the grid? Top one, here's what we've got. Everything's coming from the generation to the substation. So we're coming out at, say, 138,000 volts, cut down to 13,000 volts. Transformer, 3 houses, transformer, 3 houses, transformer, grocery store, whatever. Some of these have storage now, some have their own solar and so forth, but for the most part, this is what we're looking at. But in the future, you're going to be looking at the one in the bottom. Generation. One thing you don't want is all this renewable stuff to try to run a rotating generator backwards. And that's exactly what's going to try to happen if power goes into the generator. So you need to make sure that doesn't happen with this bidirectional link, and some big storage near the generation, and maybe some big renewables near the generation, huge utility size. Then you got substations. Maybe you have some big box stores that have big roofs, so they'll install medium storage to meet their power needs. And maybe they'll have medium-sized renewable systems, 50 kW, 100 kW, something like that. And then you got your residential areas with small or baby PV and baby storage, as I put it. Anyway, interesting situation. Now, who clicked that? I didn't do that. Okay, we're back at, and that's it, folks. So we can take a few minutes here if anybody wants to comment. What kind of luck are you having with any home automation devices you have? Be sure to read the note now from PDH Source, everybody. I'm going to read it. Thank you for attending the webinar. The webinar slides are on the webinar page. Your certificate of completion will be in your profile, top right corner of the PDH website page. And please fill out the review. So, yeah, if you have to run off now, we'd appreciate your review. Can't make things better unless people tell you what they might like to see different. So don't hesitate to be honest. We're fine with that. And I guess that does it, unless anyone else has any comments they want to add to the chat box or the conversations. Okay, the way to exit this, if you haven't figured that out, is there's a little person with an arrow. And if you hover over that, it's right below the microphone. Maybe you don't have the microphone on yours, but if you click on that, okay, I see some conversations here. Let me go back to the conversations. What do we have? Okay. Good, Robert, Richard, Yeah, my goal here is to try to create 2 hours worth of useful information. As a professional engineer myself, I've sat through some fairly boring continuing education stuff just to renew my license, which I continue to do. And my goal has been to make some of this stuff actually interesting. Believe it or not, even ethics. PDH has an ethics course that maybe is a little more interesting than the one that's talks about how to get your hand slapped if you do something wrong. So Brian and Richard and Robert and Stephen and another Robert and Michael, thank you all for being here today. And may your future of creating some of these fancy things that we're undoubtedly going to see, may that make you and some other people happy as well. Oh, there's some questions here. Let's see. Let's look at that. Okay. Here's the question. How would you calculate the load with a charger that modulates charging output based on real-time service load information? Well, that's interesting. If it modulates the charging output based on real-time service information, you still have to calculate the load based on worst-case conditions. But if you're able to modulate the charging output, you can define your worst-case condition, I guess, that says, okay, we're never going to exceed a certain output if the rest of the load on the system. That's basically a load management question. I think that is what is a reference on that question. So if I were to face that, I would want to know exactly how does the charger modulate your charging output, okay? What kind of information is it collecting? And then you'd have to base that and then design for the worst case. Let's see if I can expand this. No, I guess that. Oh, okay. The DCC9 charger from Canada. I have to admit, I am not familiar with that. Can you expand on that a little bit? And on questions, they come up anonymous, so I'm not sure who's asking this. I guess I would just have to, now you've got me curious, so I want to look up the DCC9. I'm going to write that down so I don't forget. DCC9 Thermolec. Yeah, I'm sorry, but I am certainly going to look that up so that next time I hope we will have that answer. Okay, so I guess it's 12:05, lunchtime for everybody. So I'm going to leave the session myself. When you click the leave session, you want to leave the session. The session will be ended by our friends at PDH Source.